What is state space representation in mechanical engineering systems? Imagine trying to understand how a robot arm moves or how a car suspension reacts to bumps. To do this effectively, engineers need a clear way to describe these systems' behavior. That's where state space representation comes into play. It's a method used to model and analyze how mechanical systems change over time. Instead of just looking at outputs like position or speed, it focuses on the internal conditions that define the system's current state. Think of it as capturing the system's status at any moment, including all the information needed to predict future behavior. In mechanical engineering, these internal conditions are called state variables. They often include physical quantities like positions, velocities, angular displacements, and angular velocities. These variables form a set called the state vector, which exists in a space known as the state space. Each axis in this space represents one state variable, making it easier to visualize how the system evolves. When external forces or inputs act on the system, they influence how the state vector changes over time. The core of the state space model involves two main equations. The first is the state equation, which links the rate of change of the state vector to the current state and the inputs. It's written as a differential equation where the derivative of the state vector equals a system matrix times the state plus an input matrix times the input. This tells us how the internal conditions will change at any moment based on what's happening now. The second is the output equation, which connects the system's measurable outputs to the current state and inputs. It helps us understand how the internal state translates into observable variables like position or velocity. This approach is very flexible. It can handle multiple inputs and outputs at once, which is common in complex mechanical systems. It also allows for the inclusion of initial conditions, so you can simulate how a system starts and evolves. Engineers use this model to analyze system stability, control, and response. For example, in designing robotic arms, they define the positions and velocities as states, then create controllers to move the arm precisely. In vehicle suspension systems, the model helps predict how the system responds to bumps and how to improve comfort and safety. The beauty of state space representation is that it turns physical phenomena into a clear mathematical form. This makes it easier to simulate, analyze, and control systems. It bridges the gap between real-world mechanical behavior and modern control strategies. Whether working on aerospace mechanisms or vibration control, this method provides a systematic way to understand and improve system performance. It's a fundamental tool that helps engineers design smarter, more reliable mechanical systems.